Hello, this video is my second in my lock design series, and in this video I want to talk about what is pick-proof, is it possible, and how do you make it. So I'm going to go through a set of slides that I've made to talk about that, but I'm also going to look at some 3D printed locks and compare it against some locks that are on the market or prototype, patent pending, and I'll also put links to the STL files and these slides in the description, so if you want to look at them separately you can do that as well. So let's get started. So what topics are we going to cover? So we're going to look at what is pick-proof, and that depends on who you ask, but we're going to make some definitions for this video. Is it possible to make a pick-proof lock? And technically, yes. How do we do it? You're not going to like the answer. We can do it, but it's not in a way that we would like. It's definitely not ideal. So we'll get into all of that. So what is a pick-proof lock? And this is something I've wondered myself for many years, and my own definitions have changed as I've learned more about locks and I've thought about the problem more. I used to think that a pick-proof lock was one that used staging, kind of like a clock. The perfect lock is a clock. That's not entirely true. I think that is definitely a very helpful methods for securing the lock, but doesn't make them pick-proof. And then I thought, oh, well, all the components need to interlock and be checked as a whole. I also think this is extremely helpful for making pick-proof, or difficult to pick locks, I should say, but not truly pick-proof locks. And so what's next? Well, I'll tell you what I believe now is required for a pick-proof lock. There are different opinions about what pick-proof is, and I want to talk about that a little bit real quick. So here's some things you may have heard or may hear. One that can only be opened with the key that was made for it. One that cannot be opened with lockpicks. One that has perfect tolerances and therefore impossible to manufacture and therefore is impossible to have pick-proof lock. One that provides no feedback. One where the easiest method to pick open is to try all possible combinations, brute force, and therefore manipulation is no easier than trying every other possible key. And that's my personal favorite definition. And then one that will permanently lock if an attempt to open it is made with the wrong combination. So which of these definitions is correct? Which one of these locks is pick-proof? All of them. None of them. It's personal opinion. They describe different aspects of lock security that may be desirable to different users. It is a undefined term that different people will have different definitions for. One of the things I thought was interesting when I asked, I talked to Andrew McGill a little bit about his patent pending lock, because I was designing a lock at one point, and my design ended up being so close to his. I didn't think it seemed like it would be a patent infringement, and I just said, okay, that's no good. But I emailed him and let him know that I thought it was cool that we sort of, the ideas were so similar. I thought it was cool. And anyways, I was asking him some of the stuff about his locks, and one of the important points that he made is that he's actually never called his lock pick-proof, which I thought was interesting. But we'll cover that some more. We'll look at all that a little bit more. So anyways, for now I suggest a new method to describe the security of a lock, using manipulation resistance classification. And the idea is to describe different aspects of a lock security based on the lock design, not based on attack time, because different attackers or penetration testers are going to have different skill levels in different areas, and they may have different results. And the idea is also to have a higher score equals higher security. So we have an easy to understand system. Even if you're not interested in locks, you can get an idea of how secure that lock is, and a higher score will mean it's a more pick-proof lock. So here's a table I made. You can check this out. I'll put the link to the slides on it. Essentially, what I've done here is I've taken a scale going from 1 to 9 here, where we look at different aspects of the lock and we say, okay, does it have this characteristic? And we can grade it from 1 to 9. Not all of them go all the way up to 9, as you can see. Some of them go up to 4 or to 5. And then as we go from left to right, what I consider the items on the left to be the most important and the items on the right to be the least important. And I'm going to go through it real quick with you. This video is going to be a little long, I'll warn you. So I'm just going to go ahead and cover this table though, because I think it's useful when we're assessing a lock security, because a lock security is based on a lot of things. It's not just one item. And this is really only looking at manipulation. This isn't even looking at destructive attacks. This is just looking at non-destructive attacks. So I'm going to try to go through this real quick so you can see it. And this is just something I've thrown together. If you have ideas for how to improve it, please let me know in the comments. I think it would be cool if something like this was adopted by either industry or the lock sport community, where we could grade a lock a little objectively. So the first column I have is bypass possible? If you can bypass the locking mechanism where it doesn't actually matter what position the pins or tumblers or discs are in, then the other features don't really matter, to be blunt. So the first question is bypass possible? Yes. No tools required? Yes. Tools required. Some configuration dependent. That could be like handcuffs, whether it's double locked or single locked. And then bypass possible? No. With no being the ideal case. The next most important column I've got here is lockout features. Does the lock itself out? And the categories would be none. Temporary time-based, I believe that's what a lot of banks use. Temporary time-based after failed attempts, you see this on a lot of phones. Permanent after multiple failed attempts, I believe that's how the iPhone does it a lot. And then permanent after a single failed attempt. I don't know of anything that does this. Maybe, what is it, the Siegel Hines lock? Maybe that's technically would be one of these. I'm not sure if it's actually permanent or not. But I think this is a level of security most people don't actually want. They don't want it if they put the wrong key in. The lock can only be opened destructively. But I put it there because that is a higher security level. The next two categories are feedback and unique keying combinations. And I put feedback in front here because I think it is slightly more important than unique key combinations. But I do believe that these two go hand in hand. If you have you have a ton of feedback, but you have an incredible amount of combinations, you can run through those combinations really quick. If you have absolutely no feedback, but you've only got one or two combinations, it doesn't matter. You've got a latch, you've got a bolt. You have something that can be opened very quickly. So technically I put feedback in front, but really I think these two go hand in hand. Both of these values are extremely important. And maybe in an ideal scale, it would account for that and mix them together. But for feedback, I've got direct individual feedback. When I say individual, I mean an individual pin, tumbler, wafer, disc, dial, etc. So direct individual feedback with false gates. Indirect individual feedback, indirect individual feedback with false gates. So direct versus indirect is, can I take a tool or with my own eyes directly feel the gate? Whereas indirect, I can't directly do that. Direct, I can. Group feedback is, I don't get feedback on an individual disc or pin or anything. I get feedback on the group as a whole. And then we also have group feedback with false gates. This is typically what you see with safe crackers. They're going to tend to be in this category here. And then no feedback at all, which I think is what we often say doesn't exist, but we'll get into that more. Unique keying combinations, I just have these go up from 1, 100,000, 10,000, 100,000, million, 10 million, 100 million, 1 billion. Keying resettable. I think this is important as well. So we've got a few categories here. No, not resettable. Original equipment manufacturer retains a record of the keying. That's worst case scenario. You can't change it and somebody else knows it. Yes, but OEM manufacturer retains a master backup, so you can change it, but there's still a backup. Next one, manufacturer does not retain a record and you can't change it, so at least only you know the number. Next highest group would be the OEM manufacturer does not have a backup. You can reset it, but it requires tools or training like a locksmith to help you. Next category up after that would be no original equipment manufacturer, master backup, and reset does not require tools or training. So this would be like your smart key locks. That's nice because you can very quickly change the combination if for some reason it gets compromised. So that's a nice security feature. Staging, what I mean by staging is, do you have to go return items to a state they were either a baseline state or the lock to a baseline state. So this could be very simple, like having to slightly turn your turning tool backwards for counter rotation, like some reset required for an individual pin, or it could be happening to reset a safe dial to some, baseline state up here on 5. So the categories I have there are some reset required for individual, individual must return to baseline, some reset required for group, group must return to baseline. And some of these I'm not actually sure if I've ever seen, like an individual must return to a baseline. Not sure if I've ever seen that, but I put it there as a possibility. For obstructions, what I've got here is this is sort of, well, I'll just read it out and I think it'll make sense. So no obstructions, just a clear keyway. Then I've got warding or a paracentric keyway is the next level up. After that, curtain, followed by keyway inaccessible when keying is checked. I believe there's a bike lock that works this way. I can't remember the name of it offhand right now. No keyway, but ports are available to access the locking mechanism. And then the highest one would be no keyway, no port available to access the locking mechanism. And that could be like your safe dials there. And then detection. This is kind of falling outside of the scope of manipulation, but I thought it was relevant. And depending, I feel like it is slightly manipulation relevant, so I went ahead and included it as this last category, with the lowest one being none, the next level being yes, but reset with correct key. So this might be like the Chubb detector. Then the next would be like yes, local indication cannot be reset. So this might be like your Internal Revenue Service seals. And then the next highest, or the highest one would be the yes, remote indication and cannot be reset. So this would be like what you're starting to see nowadays with like your email notification that somebody's tried to access the house or something like that. So this is my table. I'm very open-minded to making changes or things like that, but this is what I put together as to try to make something objective for classifying locks. And here's some example scores and ranking I've put together. So what I've done here is I've taken these first three, relatively low security. We've got Schlag 5-pin lock, standard 5 pins. You can see the score I gave it. The master combination padlock comes up slightly higher. And then the Schlag 6-pin combination lock comes up slightly higher as well. Let's see here, 2 and 4. So it's category 3 that put that one higher. That's the feedback level. The feedback on the standard pens versus the combination lock. And then this one took the higher level because of the number of combinations compared to the master lock. But all in a generally low group because they can all be bypassed with the 2-pin tumblers being bypassed with bump keys and the combination lock being bypassable with the padlock shim. So counterintuitively, this puts the Brink Sesame lock ahead of them with the 4 dials and the 1,000 combinations or whatever, or 10,000 combinations. But still, it's not intuitive, but that will take longer, generally speaking, to open than to use a padlock shim or to bump the lock open. So I don't think that it's completely wrong that you see the Sesame lock above these 3 other locks, although it's probably not intuitive. And then the next one we have up is a classic Abloy disc detainer. I think this is probably getting to the level of security most people believe they have on their house when they have these Schlag 5 pins. And then above that, we've got the Enclave by Andrew McGill. I made some assumptions about the number of pinning and positions on it, and I haven't seen any false gates. And because that, the Enclave by Andrew McGill sort of takes the pin tumbler out of this lower grouping here in its feedback and moves it up into the safe dial area feedback. And this was opened, I believe it was opened by Georgia Jim a year ago. He was able to pick the Enclave lock. I'm curious, and I'm not trying to hate or anything like that. I am curious if he would be able to pick the lock with without seeing the key, and how consistently he can do that. I mean, I'm not trying to hate, but I'm just thinking that was a 1 sample size. I'm curious how repeatable it is. I think he had mentioned that he was starting to notice some difference in the rotation. And in theory, you should be able to notice some rotation. However, looking at the design, it seems like it would be an incredibly small amount. It would be a very fine amount to notice. Not that I'm saying you can't. I'm just saying it would be extremely difficult. So I am curious how much feedback you get through that. But in theory, technically, there should be some minute amount of change in the rotation of this, just like you would see with a safe dial. But definitely pushes it out of this general pen tumbler region up into a much higher level. And I mean, it would be very easy to add false gates and then put this at one of the highest levels there. Yeah. So that's a general scheme of the scoring, just to give you an idea. All right, so now that we've gone through all that, what's a pick-proof lock? All right, so as we saw on the chart, there's a lot of different items that go into a lock's manipulation resistance. So to different people, pick-proof can mean different things. That being said, feedback is what enables attackers to reduce the number of combinations we test when picking or manipulating a lock. If there's no feedback and no alternative bypass, we are forced to try every possible combination. This is the equivalent of asking the attacker to try using every possible key. For this reason, I think feedback is a good point to concentrate on for pick-proof. I think this case right here, asking the attacker to try using every possible key, would essentially be what a lot of people, a lot of users, would consider pick-proof. Although that may not be true. Some people may be like, no, that's not my definition. But that's the one I'm going to concentrate on. And in that effort, the idea of eliminating feedback. Okay. So how do we do it? Let's get into some lock theory. And this is theory. This is my theories. If you disagree with me, please comment and let me know. None of this is set in stone. Okay, so how do we do it? All right. 1, it is a common myth feedback cannot be removed from a lock. It is difficult to remove while maintaining high key combinations. Okay. When we try to have multiple parts representing sections of every possible combination, we are trying to compress information. We are saying in some cases information is not important and can be ignored, and in other cases we must act on it. In mechanical terms, this means in some cases more energy is required by the system than others, depending on if the correct combination was entered. Because an attacker can monitor the energy they are putting into the system, they can identify if one combination requires more energy than another. The system could provide its own internal energy, springs, batteries, etc., such that an equal amount is provided by the attacker. Even still, the work performed internally partially exit the system and can be measured, forces or heat exiting. This means any time we try to compress combinations into a series of true, false, or otherwise smaller set of conditions, in theory, there is some feedback. Using our scale, in this case, the highest ranking one can achieve for feedback is a 6. So if we look back at this chart, the very highest we can go is up here to group feedback with false gates. To remove all feedback, we must not compress information or represent combinations as a series of true or false conditions. And this is what locks do everywhere. And I mean everywhere. I really, really like this design, but I believe it also does this same thing. I am not aware of a lock. Well, I will show you some locks that technically meet this definition, but you're not going to like them. I'll show you here in just a second. You're not going to like them. But what we think of as a lock in a classical sense, I can't think of anything that meets this. This means anytime we have something where we summarize a section, combinations, the first digit of the combination is checked as true or false, and then the second section is checked as true or false. Where there's separate pieces representing these sections, those will not work. If we have a series of cases, like even if we build a series of perfect locks, That's goes along with the same issue right here. Even if you made a series of perfect locks and tried to put them in series to represent a more complex lock, then there would also be feedback by this theory. Yeah, because you would see different amounts of energy consumed by the system, whether or not one lock at one point in the series was opened or not. And that would represent a wide set of combinations. It might be better to draw like a tree diagram to show that at some point, but hopefully that makes some sense. Okay. So, how do we make a perfect lock then? If we can't compress information in any way. A single component, part A, must uniquely represent every possible king combination. And this might remind computer or crypto people of a one-time pad. And I think there is some security overlap there. But I'm not smart enough to know exactly what the comparison is there, but I feel like there is definitely some parallels going on there with a one-time pad. But multiple components can move it. So we can have some object that represents every possible combination. And many things can move it, but it must be one single object that has all of those combinations. The position of part A, moving along one or two axes, determines if the king was correct or not. So how it's positioned will be true or false. A single component, part B, must check the position of part A by moving in a perpendicular axis to the movement of part B. So if part B moves like this, if part A is moving like this, part B can go like this. It's going this way. It can go this way, or it could go this way, downward into it. If part A were moving like this in sort of a circular shape, part B would still go in this direction, perpendicular to it. Okay. The points of contact between parts A and B must not overlap for multiple positions or combinations. So on part A, there must be a unique area for every possible combination that does not overlap with another part. And you do that by saying that there is a middle ground and an undefined region or a threshold or tolerances, but you specify there is a gap between these two areas. If they overlap, the differences in solid surface area could provide feedback. All right, so having seen all that, can you think offhand of a perfect lock? That's what you're not gonna like. A single pin, wafer, tumbler, dial, disc, etc. lock is the highest level of feedback resistance. Ideally, the single pin, wafer, tumbler, dial, disc, etc. would uniquely represent many thousands of combinations. So what that means is, pick resistance-wise, as far as feedback is concerned, just feedback, not combinations, feedback, a single pin lock or a single dial sesame lock would have the highest resistance. I made a few of these just to sort of go through an example. I thought it might be fun to go through a lock design example, and I wanted to do that with y'all. It may be a little bit of a tangent, but if you've gone with me this far, maybe you'll be interested. So what I've got here is a small, making our pick-proof lock, our very simple pick-proof lock. We've got some parts here. We have a housing right here. We have a dial with a gate in it. Nothing else. And we have our bolt. And the bolt can slide in this direction here to open or close. And when the gate is at the correct position, the bolt can go through. What makes the feedback on this ideal is that the quickest way to check the combinations is to check every possible combination. As I spin this, I don't get any information about the true gate position until I reach it. And that's what makes this feedback ideal. There is no indicator to me as this spins that we are closer or further away to the true position. There is no feedback. And this is the ideal case. In this particular, the obvious issue here is that we have, 10 combinations on this dial. But for now, we're going to ignore the 10 combination issue, and we're just going to look at it as a lock design issue. Because I'd like to sort of go through the lock design a little bit further with you. Just because I think even when we have this, there's more to it, and I guess I kind of want to stress that as well. So we have this lock. We've made this our one disc lock, and we can open it, and we can turn this, and we can prevent it from closing, or we can turn it and keep it from opening. And that's what this very first one I have here is. That is that lock right here. So some of you may be saying, well, hey, hold on a second. I know ways to bypass this. I've done some different puzzle locks online. And I'm going to show you sort of real quick how some people actually do bypass these. So here is I'm sorry, I don't know the true names for them, the gates off of a Brinks Sesame dial lock. And this is something you can actually see in different puzzles. But what I'll do here is I'll try to mix these up a little bit. And what I'm going to do is I'm just going to shake them. And hopefully we'll see the effect. It doesn't always work perfectly. But hopefully it'll work on camera for us. Okay, it's starting to get there. I'm not sure if you can see that, but eventually what will happen is the dials will start to line up. Just based off the frequency of the shaking and the weight distribution of the gates. Eventually, if you shake these long enough at the right frequency, the gates will line up. So how do we prevent that? There's different ways to do it. You could consider trying to mill the gates differently and put in false gates and things like that. But the very easy way to prevent that, and what they have in these Brinks locks is you actually, excuse me, you can see these holes drilled down at the bottom here. That's where they would put a spring, a small pin like this one, and that pin pushes up into the dial, pushes up into these little notches here. And that does a few things, actually. It prevents these from freely spinning. It also makes sure that you get good tactile feedback when you're using it as a user. You know you've got it at the right position, and it won't move when you put it there. And it also makes sure that when the user resets this, that it's not at an in-between point, and it doesn't slip on them while they're resetting it. So there's a lot of good reasons that this is actually a pretty good method of dealing with that. And ideally, you just have it in such a position where the user would not, an attacker would not be able to manipulate it and push it down and then do that sort of vibrationary attack. I planned on showing that in my example model, but I actually didn't think about it all the way through. And if I drill out, excuse me one second. If I drill out the plastic here, I don't have anything to sort of catch the pin and the springs. This is not a solid block, so it would not work the way I was hoping to show. But for our purposes, imagine that I've drilled this, I placed a small spring and a small pin in there that'll keep this from spinning. And that's how you would deal with that case. And you can actually see in this one, no matter how much I shake this, actually, there's a lot of friction on here, so this dial doesn't spin. So that's one bypass we prevented. But you may be like, well, I've seen a lot of videos on this. That's not the only way to bypass it. We can use some feeler gauge, and we can go in on the side, and we can go in and we can feel for that little notch right there. We can feel for the gate. So the second thing we can do is, I don't know if you can see that well on the camera. Let me see if I can get a view there. We've added a little ridge, a little cylinder on both sides of the disc. So we've gone from flat, and now we've added a little ridge there. And the idea here is we prevent that feeler from going there. We block it here, and then, and let me see if I can find this one right here. And then we modify our housing to cover up that area. So you'd actually have to really bend something quite hard. You'd have to do, let's see here, so 1, 2, 3 90-degree turns to feel that gate. So that's a good way to increase the resistance there to inspecting it. And that method right there, that would not be a bypass. That would be a feedback that would fall into, sorry, one second, let me grab my chart again. Yeah, so the vibration would fall into a bypass, and the gate would fall into direct individual feedback right here, the bottom one there. So we can prevent that with that little loop set up there. And I believe that's this one. Yep. That's what I've done with this one here. I'm not going to get out feeler gauge to show that to you. So you can just sort of take my word on it. That's one way we can improve this. And you can see that actually that is not something they do on the Brinks one. So that is part of the reason that using those feeler gauges is a valid attack on the Brinks one. But we can still take this a bit further, because even with this case right here, even with preventing the feeler gauge from going through it, all we have to do to try every possible combination is literally just, this one's a little stiff, but we can just spin through the dials, and eventually, when we get to the correct one, it'll fall open. So that's a pretty quick process. One way we can prevent that and make that take longer is by using staging. And this is saying that we require some sort of reset before we go forward. And in the case of a sesame lock, that can look something like this. So I'll show you. So before, we upgraded and we had just the ring. And now what you can see is we have notches for every possible combination where the bolt can start to go in, but it can't completely pass. Now what this does is it locks it in place, so we can't continue to spin the dial. We have to pull the bolt back, then we can rotate, and then we can test a new position. Pull it back, rotate, test a new position. And this prevents us from sort of just continuously in a single motion testing multiple combinations. And this is a good way to delay or make picking take longer. That's essentially what the staging does. I used to think it did much more, and you can use it to do more, to reduce more feedback, but it is limited. It is not, in a truly theoretical sense, it is not able to completely isolate components, because at the end of the day, the total energy going in and out of the system is the same, whether or not it's instantaneous. I'm sorry, that wasn't very clear, but here I'll show you an example. And on this one, you can see the glue got a little bit of my finger on there, and yeah, the glue definitely messes it up the look a little bit. So you can see here, if I drop it down, this one goes further down than this one, if it's at the incorrect combination, because it's falling into what you could call it a false gate on every single possible position. So every position has a false gate, or you could call it some kind of interlock. But you can see it goes down further, but it doesn't fully open. And if I try to turn the disc, I am blocked. I am not able to. I have to push this up, and then I can rotate it, and then I can try a new combination and open it up. And that's using staging. So I think that's neat, and I haven't you can see with these, you may not be able to tell, but this isn't using staging. These are, the reason this has notches in every position is so that you can change the combination when you rotate this. It allows you to change the combination. If you look inside this piece right here, this is where you can see we only have one notch. And that was where you would need to have the multiple notches to get that staging effect. Yeah. And here is, you can take a look at Andrew McGill's. The way this one works is if we were to enter the wrong combination, we would get some rotation right here on Enclave. At this point, this is like that. We can't continue to go. We can't lift individual pins. We have to reset this backwards and make our adjustments, and then rotate forwards again to see if we've made progress. And in theory, the amount that this rotates, we have to somehow be able to measure or detect some difference in to tell whether or not we're getting closer or further to opening the lock. So if we were to compare these on my lock scale, and this is something I also want to show as a sort of a, I want to mention this as a warning, I guess, so like an issue I already see with my scale. But technically, this lock right here would qualify as pick proof with its 10 combinations. And on the scale I have right now, because feedback is rated higher than combinations, this would get a 7 for feedback, even though it would get a 1 for combinations. And this would be ranked higher than all these other locks on this list. Now, obviously, this is not a better lock than all the locks on this list. And so what I'm trying to mention here is that these two categories go hand in hand. They're both extremely important, that we want a very high value for our feedback resistance, but we also want a very high value for a number of combinations. One of these is not useful without the other. High combinations with tons of feedback is worthless. Well, not worthless, but of limited value. Great feedback resistance with only a few combinations is not of a lot of value. That's when you're talking about latches or baby proofing something, So the ideal lock will score both very highly for feedback resistance and for unique key combinations. And the problem, as we mentioned before, with a pick-proof lock is you can't compress those key combinations. You have to represent them all on a single piece of material, which is not, you can't compress them. And yes, you could interlock different pieces to form a single solid piece. You could do that, but you cannot, you can't summarize a section as true or false. It has to be interpreted as a whole piece. You can't check one section or one disc. It can't be a series of true or false questions, even if it is a series of perfect locks. So what that means is we have to have really big pieces. We're going to have to make these larger pieces to represent every possible combination. We can't do it where, like, normally with a pen tumbler or with a sesame lock, we can have some value of like the number of possible values, like 0 to 9 or 0 to 6, raised to the exponential power of the number of different discs we have. And so that lets us get a very, very large number of combinations by adding more discs in a row or more tumblers in a row. We can't do that with an ideal pick-proof lock. We have to put them all in a single piece. And so I'm assuming that ideally that would be some sort of two-dimensional plate. But even that's quite large. And so you're limited by your tolerances. So it's a difficult problem to have a truly pick-proof lock and get these really high combinations. And it's difficult to get into these categories and also maintain these high combinations. That's why this Enclave lock is special, being in this category here, getting this sort of safe dial level of security while still maintaining a high level of combinations, when the vast majority of locks we see are down here. Yeah. So I think I covered that. I think that probably makes sense to y'all at this point. And I think that's probably intuitive in a lot of ways. That makes sense. Okay. All right. So end of lock design video number 2. Don't cry. We are finding methods to make pick-proof locks. So this is progress. Progress is occurring. With electronics, memory buffers can uniquely represent large combinations, enabling pick-proof designs. When we start looking at electronics, it becomes much more possible to make these pick-proof designs. That being said, electronic locks can make many of the same mistakes as mechanical locks. And in theory, there is some overlap with the theory of mechanical locks, where you can monitor electronic systems and see how much energy they're consuming to see how likely something is as far as a correct password or incorrect. So there is some overlap there as well. It's very different, but there is overlap. It is reasonable to expect locks can still be pick-proof and practical applications with group feedback, false gates, and feedback limiting techniques. What I mean by that is if you took this lock right here, threw in false gates, threw in some sort of buffer, or maybe some sort of spring-loaded buffer here on how much this can rotate, I would have a very difficult time believing that there is a device that can measure the difference in positions well enough that you could decode this lock without spending an exorbitant amount of money on sensors. I mean, technically, in theory, still decodable. However, in practical application, not really. And there's a lot of locks out there like that. Even and I should probably go ahead and correct myself. At one point, while talking about lock design video 1, we talked about how even a pin tumbler with perfect tolerances is technically pick-proof. Because you can measure the difference in, let's see here, the difference, the different amount of force it requires to lift each pin. If you were to lift one pin to the correct height, you would see a distribution on the others. That's true even with perfect tolerances to an extent. If you had an infinite number of pins, the amount of feedback would approach 0. So in theory, an infinite number of pins will also push that feedback to 0. But we can't have an infinite number of pins. However, we can have so many pins that for all practical purposes, you can't tell. So there's some give and take there. There are lots of areas to significantly improve lock design and security. So there are a lot of sections here. There's probably stuff I'm missing that y'all think I should add. There's a lot of stuff we can talk about. I'm curious, what would y'all like to talk about next? I can keep talking about stuff like staging and interlocking components, things that I think are super helpful for making high security locks. Or maybe there's something else that is of interest to y'all. So let me know what you think. Hopefully this was enjoyable and not too much of me just talking your ear off, but it's already coming up on 45 minutes, so I'm going to be kind and shut up. Thank you all for watching. I hope you enjoyed that. I hope you took something from it. Yeah, thank you.